about Ampere's law, I want to start by reminding us of the things I think you should memorize. This is for Grace's benefit and for the rest of the room's benefit. There are some groups of things you should just memorize. After you prove them to yourselves, you should take note and memorize them. And I want to go through them in terms of first E field, and then I'll go through B field. For the electric field, remember, we're talking statics. So for the electric field, you should have the electric field for a point charge, Q, located some distance r away. You should have the electric field for some spherical charge distribution located a distance r away. And you should note that they're the same answer. Going on for the electric field, you should have for a long, uniformly charged object, like a bar, you should be able to note the size of the electric field a distance r away from the bar, assuming a very long bar compared with the distance away from the bar. So this is the infinitely long charged insulator. And it should be noted that what you're looking at here is something that's proportional to 1 over r. Get the constants right, and you'll be okay. You know, the point charge is 1 over r squared. The bar is 1 over r. And last, you should know the electric field a distance r away from a sheet of charge. I don't know how to even draw this now to do it fast. That's not it. So if I have an infinite sheet of charge and I am some distance r away from its surface, assuming the sheet has a charge sigma, you should know what the size of the electric field is, a distance r away. And it should be within your knowledge that it doesn't matter how far away I am, that the electric field near an infinite sheet of charge is uniform and not dependent on how far I am. The last thing about electric fields that you should know is that if you have a large conductor, I don't even care what the shape is, it could be a sphere, it could be a box, you have a large conductor, large solid conductor. You should know the electric field near its surface and note that it's half of the infinite sheet. It's half of it because you have half the charge available, yeah. Because there's no electric field on the other side when you do Gauss's law. So the electric field on the other side is 0. So when you have a large conductor, the electric field here is half that of the sheet. All right. For magnetic fields, there's less to memorize. For the magnetic field, you should note the magnetic field at the center of a current loop of current I and radius r. So the magnetic field at the center of a current loop of radius r and current I. Buzzing. For a long, straight current-carrying wire, you should know the magnetic field a distance r away from the wire. Now, I'm encouraging you to memorize all of these. It's worth memorizing. The time you will save on the exam is exceptional if you have these memorized, and do not have to second guess them or make them second nature. Make note cards and memorize these shapes and these particular situations and commit them to memory. Doesn't have to be for the semester exam. It really should be for the AP exam. All right. Ampere's law. We were talking about it Thursday. I'm going to reiterate what we have for Ampere's law. Ampere's law and Gauss's law are incredibly similar. Ampere's law has two sides, just like Gauss's law did. But Ampere's law states that for any closed loop, the sum of the magnetic field along that loop will be equal to the enclosed current inside that loop. For any closed loop, the sum of the magnetic field along that loop is equal to the enclosed current inside that loop. So, if we have some long, non-uniform wire, it doesn't have to be one wire. It can be thousands of different currents if I want. But I have one long, continuous wire for this example with current I passing through it. Then I can wrap what's called an Amperian loop around the outside of that wire. My Amperian loop is like a Gaussian surface in that I choose the size, I choose the shape, I get to choose the location, but the Amperian loop is a structure that doesn't really exist. I create it for the purpose of my calculation. But the goal of the Amperian loop is similar to the goal of the Gaussian surface. The Gaussian surface was to add up all of the bits of the electric field that traveled into or out of the surface. My Amperian loop is to add up all the bits of the magnetic field that circulate around the outside of the current. The problem is that this is what's known as a line integral. And we've been doing line integrals this year in this class, but a line integral is simply a way of summing and getting a length. It should note that for any shape, if I sum individual pieces of the length, I get the entire length. That's not a surprise. So if I sum up all the centimeters of a meter stick, I get a meter stick. That's what this integral is telling us. That part's not the part of the line integral that's interesting. A line integral usually has some other condition placed on the length of your sum. And in this case, the condition is to evaluate how much of the magnetic field is directed along the length of your Amperian loop. This is a dot product, and it is an important dot product. It states that the only contributions to this sum are contributions of the magnetic field in the direction of your loop. The only contributions to the magnetic field are in the direction of the loop. So for what I've drawn, I hope you guys realize that the magnetic field around this loop, using the right-hand rule, has to be going into the board on this side and out of the board on that side. You guys follow me on that? You guys use your right-hand rule and verify it? So the Amperian loop that I've drawn, there's going to clearly be a place here where the magnetic field will be in some direction, and ds will be in another. Now I'm just looking at a small piece of the length of my Amperian loop right there. In order to compute Ampere's law, I have to compute each product of the magnetic field and the piece of length throughout the entire closed loop, summing up basically all of the bits of the magnetic field that circulate around the outside of this current. If I can get them all, then I'll have something that will compute the entire enclosed current. That's the nature of Ampere's law. Now, usefulness of Ampere's law is actually far narrower than Gauss's law. There are some interesting things about Ampere's law, some that are unique, but generally, we use Ampere's law in a similar fashion than we used Gauss's law. One of the fashions is to determine the size of the magnetic field, or to create an expression for the magnetic field around symmetrical current systems. However, it should be noted that there is just as many, I don't know what the word is, even though I'll put in here. It is hard to come up with situations where Ampere's law can effectively find the magnetic field, because we can only use it in cases where there's enough symmetry for us to actually compute this integral. Or worse, the kind of symmetry where the magnetic field is constant everywhere on my current loop. It's just hard to find situations where Ampere's law can work. In similar fashion, it was hard for us to find situations where Gauss's law works. Most textbooks and most examples in physics provide us with 3 situations in which we can use Ampere's law effectively for, I would say, real-world applications. There's the single straight current, so a long wire. There's the solenoid, whose length is much greater than its width. And then there's the toroid. This is really it. There's just not a lot of ways to use Ampere's law. Now, saying that, there certainly are a lot of ways for exam writers to trick you about Ampere's law. And what I mean by that is Ampere's law, like Gauss's law, isn't about the magnetic field directly. It's about a condition that exists. If you remember, with Gauss's law, Gauss's law was Q enclosed equals epsilon naught times the flux. So there are quite a few problems that asked you to talk about flux. Do you remember that? Where you would have maybe a couple of charges, one positive, two negatives, and they would show several different closed surfaces. Remember these? Asking what's the flux through surface number 1? What's the flux through surface number 2? And you'd be like, well, I don't know what the electric field is. And they would make you think you were calculating flux when all you were doing was adding up the charges. Do you remember that? Well, you realize we can do that with Ampere's law too. In Ampere's law, one of the first things you'll tend to see, in like practice questions and such, are problems that have several different currents. So perhaps there's a current here into the page, that's 2I, and a current here out of the page, that's I, and a current here that's out of the page, that's 2I. And then they'll have this Amperian loop and this Amperian loop, and maybe even say this Amperian loop. And they'll ask, in which loop is the enclosed current 0? Or in which Amperian loop, or in Amperian loop, the yellow Amperian loop, what is the enclosed current? The problem is that it can't be as tricky because we don't have a word like flux to throw in there. So they might ask, in which of these loops is the line integral equal to 0? Or in which of these loops is the line integral equal to 3I? They'll ask questions like that to try and throw you off that the line integral is equal to mu naught I enclosed. That is the line integral. All right. Tomorrow we're going to talk about the solenoid question.